Alright, so let's finish this problem and answer questions C and D for this population model, this piecewise linear population model. So part C says, according to the model, when was Detroit's population 1 million people? Now remember that our model is in thousands. So let me go back to that just to remind you. All right, so thousands. So a million is 1,000 thousands. So what we're trying to do is find the intersection of this piecewise linear model with the height 1,000. I want to draw a picture to kind of illustrate. Well, actually, we've got a picture. Let's just use the one we have. So here's the situation. Let's say 1,000 is, I've kind of got a bunch of stuff on this. Let me erase this just so I have room to draw this. Let's say that this is the height 1,000. So we draw this dotted line over here, and we see that we have two intersections. One when the population was increasing, and then another intersection when the population is decreasing. So we actually have two calc intersections to think about. And we could do this separately by doing calc intersect with y2 and then do calc intersect with y1 and do that as two different problems and find the intersection point. But we could also do this all in one fell swoop. So let's try to do that. Let's try to find both intersections more or less at once. Okay, we're still going to actually have to do two steps, but well, let me just show you what I mean by that. First of all, we have both functions entered in the function menu, and let's look at our window. So we need to actually start in 1900. And let's let our x max, actually that's probably okay for 2010. Our y min and our y max though, now we know that those aren't gonna be right. That's from the previous example. So we could go to the table, or we could actually just take kind of a guess. And if I was going to take an educated guess at this, notice that our initial population is 285. So if we started at, say, 250, that's 1,000, and we want to know when it intersects 1,000. So if let's say that I go above 1,000, maybe to like 1,500. That might be too big, but at least we can graph and see. So these are just rough numbers that I think will be big enough or small enough to give me a decent window. So let's graph it and see what we see. Okay, now I just realized that I forgot to actually graph the height line 1,000, so we'll have to do that. But nevertheless, look at our picture. So we are seeing basically the correct picture. We've cut it off at the top here. So if we wanted to see more, we'd need to go above 1,500 because that's where we stopped. So that's that means that our y max was too small, but maybe it's still big enough to see the intersection. Let's go ahead and add that in. So I'm gonna stick 1,000 in for y3, and let's give it a graph and see. There we go. That's actually pretty good. So I can actually see all my intersections now. From here, we just need to do calc intersect. So let's go second, trace, number 5, or intersect. And in this particular problem, this whole first curve, second curve business is actually pretty important because we have multiple curves to deal with. So we need to pay attention to where our cursor is. So we kind of have to find it, unfortunately. You see it coming down there? So it wasn't exact. I was kind of thinking it'd be over here, but it was in this curve. So if we are trying to find this intersection, then we need this curve and this line. But if I'm trying to find this intersection, then I need this curve. So be careful. So let's say that I want to, since it's in this curve already, I'll go ahead and find this intersection first. And that's is the second curve that I'm interested in. You have to also understand when I say curve, we just mean the function, so it doesn't actually have to be curving. So there's my guess. And there is our downwards intersection in 1994. So let's write that down. Actually, I'll put it up here. That's 1994.63. Okay. Now I'm going to go back to my calculator. I want to find the other intersection. So let's try it again. And now we've got to be sure that we are on the correct curve. And you see now where I am. I'm moving over. I'm going to move my cursor over and navigate to this upward sloping curve. That's my goal. Okay. Actually, I should have been paying attention to my numbers down here to tell me what was going on. Because actually, look as my x values get smaller, my y values are getting bigger. So I'm moving this way, but I'm going up. So that means that I'm on the wrong curve. I need to be on this one. So I need to mess around with this some more. So there's my cursor. So I'm going to press down one more time. And now I'm on the right curve. So I had a little trouble getting it in the right place. The up and down buttons move me from curve to curve, and the left and right buttons move me along the curve. Okay, so that's actually useful to remember. So there we go. So now I'm on the first curve that I want to be. And for the second curve, let me move up. There you go. That's where I want to be. And my guess is right here. And so there's our intersection, 1922.84. Okay. So that's our answer for part C. Let's take a look at the slide solution. Okay. Notice also that in both of these we round upwards to the next year, since we are starting midway through the year. Okay, so let's look at the last question. When will Detroit's population fall to 500,000? Now, this is again going to be a calc intersect, but it's a little bit, in a way, it's a little bit easier than the previous question, because since it says fall, we are actually only going to be looking at the intersection on this second curve. So we would be looking only at whenever that hits, somewhere in there. Okay. Very rough sketch. But so we would just use y2 for that one, and we'd just do calc intersect with only y2. So let's do that. So I'll change this to 500. Okay. And let's graph it. My previous graph, I'm not sure if it's going to work or not. We will see. It does not work. See that? So I see one intersection, but it's not the one I want. It's not the one I'm interested in. So I need to change my window. What I need is a bigger X max. So I'm going to change my X max to like 2500. And we'll see if that's big enough. Okay, definitely big enough. So that's the one I want. Now we can do our intersect. And of course, it's going to be hard to see. Okay, first curve, that's fine. Second curve. This window is kind of making it... Oh, there we go. Oh, also notice, and excuse me for not saying this earlier, but it actually, you can look up here. You see that it's actually telling you what curve I'm on right now. So that would have been useful to pay attention to. So my second curve does need to be y2, so that'll be fine. And then my guess for an intersection, well, I still don't know, I can't actually see my cursor, so let's see, what am I doing here? There it is. This isn't the ideal window, but I'm going to make it work. Okay, so there's our intersection. 2020.89, we'll call that. 2020.89. Which would be 2021. Okay. So there you go. There's an example of working with a piecewise linear function. In addition to actually making one, we also work with one. Let's take a look at another problem. This is also a piecewise linear function, I believe. Suppose I travel by car for 1 hour and 15 minutes to an IMAX theater that's 100 miles from my home. I stay at the theater for 3 hours before returning home, and the return trip takes 2 hours. Assume a constant rate of change on each leg of my trip. So we want to write a model for this, where distance d from home in miles is a function of elapsed time in hours. Okay, so I'm going to start by graphing it. And my graph, the horizontal axis is going to be elapsed time in hours, and the vertical axis will be distance from home in miles. Okay. So at time 0, I guess we're going to Atlanta to the IMAX theater. That's 100 miles from here. At time 0, we are at home, and then we go for 1 hour and 15 minutes. So time 0, we are 0 miles from home, then an hour and 15 minutes, which in hours, 15 minutes is 1/4 of an hour. So this would be 1.25 of an hour. I would be 100 miles from home. So that's 100. And we're assuming a constant rate. So that would be a linear function. How do I know it was constant? Because it says so. Constant rate of change on each leg of my trip. Then I sit there in the movies for 3 hours. So for those 3 hours, what happens? Well, nothing. I don't change my distance. So that would take me to 4.25 hours where I don't move at all. And a horizontal line is what I need, because a horizontal line means that my distance does not change. And so that's what's happening. Then I turn around and I come back home, and it takes me 2 hours. So 2 hours. So that would take me to 6.25, and I take my trip back home. Okay, so in the next lecture, we will generate a function for this.